voltage regulators using Zener, BJTs, and sometimes op-amp. Another way of regulating the voltage, not in terms of voltage control, but controlling the current. As we all know, the load voltage is a function of load current. V equals IR. So if you can control the load current from going up or down, eventually you will be able to keep the output voltage across the load maintained at your desired state. Here's a configuration of current limiting circuit. So this needs some discussion. What do we have here? We have two transistors, two NPN transistors, Q1 and Q2. We have an op-amp. So here is Q1. And then we have Q2. The second one is Q2, the bottom one, second transistor. We have an op-amp right here. And then you have a Zener connected on the input side. This RSC resistor, it is called a short circuit sensing resistor. It senses the current and diverts away current. If the current becomes too high, it diverts current away from going to the load. If the current becomes low, it tries to provide more current to the load so that the voltage is maintained. Now, as we know, for the op-amp, I minus or I plus, there will be no current passing through these op-amp pins due to this high input impedance. Therefore, we have to concern on the right hand side. This IL, the current that is going to the load current, also if it increases because of its connection with the short circuit sensing resistor, when IL increases, the voltage across this RSC, short circuit sensing resistor, it will also increase. When it increases, what is going to happen? It means, as you can see, the connection here with the base of transistor Q2. The increased voltage across RSC means increasing current flow, which turns on the Q2, the second transistor. Once the Q2 turns on, here it has a collector connection with the base terminal of Q1. When Q2 is turned on, collector current is flowing, emitter current is flowing, which means at this junction, more current is going through the Q2 and less current is going through Q1, because now IB has to share with the collector current. Whatever goes as the IB1 of transistor Q1, now it is shared by Q2 due to the connection with its collector. When IB is less, now we know Q1 conduction becomes less. IC1 will be beta times IB1. If IB1 decreases, IC1 is going to decrease. IE1, which is approximately same as IC1, it will also be decreasing. As a result, what happens? The current coming out of Q1 gets reduced. The current that passes here as IL gets reduced, which means the load current is now decreased. So the output voltage remains V out equals IL multiplied by RL. Opposite thing will happen if for some reason, maybe during operation of the circuit, there is some disturbance on the load side, so the load current gets less and less. It will decrease the voltage across the short circuit sensing resistor, which means Q2 conduction will not happen. The base current will go down. So Q1 conduction will go up and it will supply more current across the resistor, which eventually will go through the load resistor as load, and then your voltage will be up. This is another way of maintaining the output voltage through current limitation. There's another type of voltage regulator known as the shunt. This is again a block diagram. We start with the block diagram. A shunt path is a bypass path. In electronics, shunting means creating a low resistance path for electric current to allow it to pass around another point in the circuit. So if you have some construction in the road, sometimes the construction workers will create a small side bypass road so that you can flow through the side and then you don't go through the construction site. Once the construction site is over, you can use the main road again. The nature of current flow is that it will choose the path of least resistance. If it sees two paths, one has high resistance and the other one is less, it will always choose the path of less or the least amount of resistance. The shunt path is creating the least amount of resistance path. So here is your input voltage, Vi. You have a series resistor. Passing through this series resistor is a total current, load current, and any bypass current, shunt current. On the output side, the output voltage is connected to a load resistor and ground. This portion is the output voltage that is sampled. The sampled voltage is fed back, it's a feedback path, to a comparator. What does the comparator do? This is V in for the comparator, Vi, and this is the V reference. Based on the comparison between V in and V reference, the comparator will send a signal. You know, for the op-amp comparator, you can have a positive saturation or a negative saturation signal. In some connections, you can have a positive, for example, plus 12 volt, and then the low signal is at 0 volt. Nonetheless, it has high signal and low signal level. So after sampling the output voltage from the load, the comparator compares it with the reference voltage, sends a control signal. If the output voltage is too high, what does that mean? The load is fixed. If the output voltage is too high, it means the load current is not normal. The load current is increasing. But if the load current is totally normal, everything is normal. There will be no shunting. All the current from the input circuit, input side, will go to the output load for normal case of operation. The shunting action will take place if the load voltage tries to change due to a change in the load. Sometimes we have a faulty load. Sometimes the resistor gets worn out, creating the risk of a short circuit or a high current. If the sampling circuit senses that there's some disturbance, which will show up as a difference between your feedback voltage and reference voltage, it will send a control signal. The control element will activate a path, a low resistance path, so whatever current is coming from your supply, some of it will be channeled to the parallel or the bypass path. Means the current that will now flow through the load will be less. That will bring the output voltage down to the level where you want it. This is an example using exact circuit. No longer it's a block diagram. Vi, as you have noticed, it's an unregulated supply. The input is not regulated or controlled yet. This is an NPN BJT with common emitter configuration. Emitter is on the ground. Also, you see how the load is connected with respect to the BJT. VL is across RL, plus and minus. If you look at its parallel node across, if you measure from the top of VZ to the bottom of the transistor, which is the emitter terminal, there is a path of current that can possibly flow. From the top to bottom, the total voltage drop is the same voltage as you will see across the parallel node. Therefore, the output current Vout or VL in this case will be VZ plus VBE. Because the parallel node, the total voltage is VZ and VBE. Whatever the Zener voltage you are given plus 0.7 volts, and Vout or VL is just parallel to it. It is called a basic transistor shunt regulator. The RS, input resistor RS, drops the unregulated voltage by an amount depending on the current supplied to load resistor RL. Ohm's law equation, the load voltage VL will be the current IL multiplied by RL. Now, if RL goes down, VL will also go down. VL equals ILRL. If you look at that equation, if for some reason you have a disturbance in the load and the resistor value is going down, almost trying to create a short circuit, RL goes down, from the equation VL goes down. When VL goes down, you see the equation on the left, VZ plus VBE. VZ is fixed, VBE has to go down. And discussed in the previous class, the graph of IB versus VBE. When VBE goes down, the base current IB goes down. As a result, IC will go down. And then what happens? The load current will go up. This is how the system works. So, a reduced base current to Q1 results as because of this connection, shunting less collector current. Thus, the load current is larger. The opposite will happen if you try to go to the opposite situation. So the summary of this shunt voltage regulator is, if IL tries to become very high, the shunt path is just through the Zener and the BJT. It will be activated. And then IL will be maintained at a safe level. If the current IL is trying to go low for some reason, the shunt path is not activated. All the incoming current will be fed to the load resistor so that you will have your output voltage maintained. But for this problem, the inner calculations are actually pretty simple. I'm going to clean up the picture again. As you can see, VL is Vout. VL equals Vout. IL will be VL or Vout divided by RL. So the current here is IL. You have to use the Ohm's law, VL over RL. The load current, what about the current coming to the initial series resistor, IS? What is the voltage at this point? It is VI. And on the right hand side of the resistor, what is the voltage? This is VL actually, parallel voltage. You can say IS equals VI minus VL over the resistor value. VL, this is VI, divided by the resistor RS, this is IS. So I'm going to put the arrow right here. IS equals, I just put the equal sign, but just I flip it by 90 degrees. What about the collector current? If you take the main current IS and subtract the load current, you will actually get the collector current. So IC equals, in this circuit, IC will equal this. IC equals IS, the main supply current. Normally, when the shunting is not happening, all the main current will go to the right. It will not go through the BJT. It will go through BJT only when there is a dangerously high level of load current. So here it is. IS minus IL is your collector current. What about IZ and the current from B to E? Any current or the base current. They are much smaller than IC. We can ignore this in the circuit. The shunt current is much smaller than IC. We can see one example on the next slide. Example 15.11. Determine the regulated voltage and circuit currents for the shunt regulator shown below. Let's find out V out first. What is V out in this circuit? V out equals VL. What value should we write? From here to here, what is the voltage? That is V out. So the Zener rating is given 8.2 volts and VBE will be 0.7. What is our V out? You add them. VZ plus VBE is going to be 8.9 volts. 8.9 volts in this circuit is the V out. Can we find the load current? The load current IL, how much will that be? Using Ohm's law, what is the load current?
VL over RL.
So 8.9 volts, we will divide by 100 ohm. If you divide by 10, it's 0.89 ampere, right? If you divide by another tens, multiply. So 8.9 divided by 100 ohm is 0.089 ampere, which means it is 89 milliampere. Let's write on the top 89 milliamp. Milliampere. Circuit currents, it doesn't really specify what current it wants. We can try to find IS. We can try to find IC. So let's find IS. VI minus V out, because this is all parallel. You see, with respect to the ground, this node, you can say 22 minus 8.9 and divided by 120 ohm. So 13.1, I think, 13.1 over 120 ohm. How much is that? bring a calculator. It is 0.1092, 109.2 milliamps. We can write about 109 milliamp. milliamp. That's the main supply current. The load current is 89 milliamp. So something is missing. The load is getting 89 milliamp. The current provided from the main supply is 109 milliamp. Where is the rest of the current going? 89 plus 20 is 109. The rest of the current is the collector current. If you take IC, IS minus IL, you will find the IC current at 20 milliamp. IZ and IB, the IZ is same as IB. They are so much small that it is negligible. If you divide, for example, what should we divide by? Should we divide by a beta of 100? So if you take 20 milliamp divided by 100, for example, you will get 0.2 milliampere. That is going to IZ. If you compare the 0.2 milliampere, I just randomly picked a beta value of 100. If I take a beta value of 50, let's say 20 milliamp divided by 50, you have 0.4 milliamp, not even 0.4 amp, it's 0.4 milliamp. Means 4 divided by 10,000, that's 0.4 milliamp. So let's say we have the beta of 50, IZ is 0.4 milliamp. This value is nothing compared to the main current 109, the load current 89, even the collector current 20 milliamp. It is 50 times less than the collector current at least. We can ignore this. Any questions? This is how you determine the IS, IC, IL, and V out of the circuit. Typically, exam questions involving the voltage regulators are like this. You will be asked, if you get a voltage regulator circuit, it is asking you to find the different voltages and different currents. So whatever we did in the class, in the previous session, and what we'll be doing in today's session should be sufficient knowledge for you to handle and answer this type of questions. The paths and the formulas are not given on the lecture slide. That's why I have to show you. So how you calculate the formula is in the previous one. If you are recording this session, you will know how to calculate it. I don't hear any questions from you regarding the current limiting voltage regulator.
No, I gotta ask you, like, where do you get the VL again? I didn't catch it.
The load voltage. VL, you mean?
Yeah, the VL or VL that you say is the same.
The output is taken across the load. So this is the output side. If you put a probe on your output resistor, this is the load. This is V out. This is the output voltage. That's why V out is VL. If you are wondering why it's 8.9 volt, it is simply you look at the parallel node. It is VZ plus VBE. From the previous slide, V out is VZ plus VBE and V out equals VL. It doesn't explicitly say it's V out, but when we put a load resistor on the output side, we take the output across the load resistor in this case. That's why V out equals VL.
Teacher, so the formula for IS and IC were given because
No,
you didn't write it
it
down.
is not in the formula sheet. That's why I had to write for you.
I mean, so the formula, this is the formula that we need to remember to calculate the IC and IS, right?
Yes, IC will be IS minus IL. That's the collector current. And IS is take the voltage difference, the potential difference across the resistor RS. It's VI minus this thing, this whole thing. This is the parallel voltage, V out, which is VZ plus VBE. So also VL. IS is VI minus VL over RS. To calculate IC, IS, IL, you have to follow these formulas. Any other concerns?
Teacher, IS is the current for the shunt, is it?
IS is the main current. The one you're seeing from the shunt is ISH that goes to the bypass. IS is the main current, which will include the current that is reserved both for shunt and for IL. When the load current is normal, there will be no shunting. This current is I shunt plus I load. IS is actually in this circuit shunt and load.
Thank you, teacher.
Welcome. You can improve the shunt voltage regulator further. In the previous case, you had only one BJT. What if you increase the number of BJT? You have two BJTs now, two transistors. This is also known as the improved shunt. When the output voltage tries to increase, what is going to happen? The Zener current will increase. We did not say the Zener voltage will increase. Zener voltage is going to be fixed, but you know Zener current flows at different levels. And there is a Zener current rating IZ max because you have a maximum power rating of PZ max as well. So the voltage remains the same, but the current can vary through a Zener. When the output voltage tries to increase, the Zener current will increase. Means, see how it is connected with Q2. An increased Zener current, the increasing current will increase the conduction of Q2. The Q2 conduction, I'll put an up arrow, goes up. And then Q1, Q2 emitter is connected to the base of Q1. When Q2 conduction goes up, this one collector will go up, emitter will go up, base is going up for Q1 as well. And then what happens? Q1 is going up as well for conduction. The voltage drop also increases. Now this current is, this is the collector current. It increases when you increase the current across. This current is increasing, it is flowing through RS. The voltage drop will also increase because V equals IR. You keep R fixed. Now I is increasing, the voltage drop will increase. when Q2 provides the larger base current to Q1, regulator handles a larger load current. Once the voltage drop at RS increases, the output voltage will decrease because shunting will now happen. Do you see how it goes from step to step? If you remember the block diagram, this current is what? I shunt and load. I shunt plus I load. Let's call it I load. Normally, all of them will flow here. The output voltage tries to increase means what? The current is more. We have a fixed RL resistor. The current is more. Then the Zener conduction increases. Q2 increases, Q1 increases. Means it is pulling down more current. It's hard to follow. I know it's hard to follow. The steps are not explained on the slide. That's why I'm explaining. Let's start with this one. I put it number 1. Something is wrong on the load side. The output voltage tries to increase because the load current is going up. As you look at the connection, this is flowing through the load, so Zener current increases. When Zener current increases, it means it is connected to the base of Q2. We'll call it stage 2. I just call it stage 2. Q2 conduction increases. Q2 is providing the base current to Q1. When you have increased emitter current for Q2, Q1 is also going to increase. When IB1 increases, it means IC1 is going to increase. Now the current, because of this connection, it will pull down more current from the main. This one is a fix. IS equals shunt plus load. Now, if you have less shunt, more current will go to the load. Now the load is becoming a bad situation. More load current. Now I shunt is more. Therefore, the load current will decrease. You will come back to the normal stage. The output equation. V out equals VL, the load voltage, and it is VZ plus VBE1 plus VBE2. So this voltage plus this, it is the output voltage. This is the improved shunt using 2 BJTs. Why do we need the Zener? The Zener provides a reference voltage. Zener is called the voltage regulator diode. Zener provides a reference voltage so that the voltage across R1, we have a resistor R1 here, senses the output voltage. R1 is connected to Zener, which is also connected to the output. This Zener is provided as a reference voltage in order for R1 to sense the output voltage. What happens when the output voltage tries to decrease? Now, output voltage trying to decrease means IL, let's call it IL. On this slide, I will just sketch IL. When the output voltage decreases, you have a fixed RL. So which one has to go down? IL is going down. It means the Zener current also going down. When the Zener current going down, the base current of Q2 is going down. When the base current of Q2 goes down, it will also provide less base current to Q1, which means Q1 conduction is going down. And then the collector current of Q1 is going down. You see the main current IS equals I shunt plus I load. The shunt is going through the collector of Q1 and the rest is going to the load. So this is I shunt plus I load. What is our problem? Our main problem now is I load is trying to go down. So what we have to do to fix the situation, we have to provide more load current, right? If you want to provide more load current from the main supply, you decrease the amount of shunt, which means IL has to go up. So now through the less conduction of Q2, which results in the less conduction of Q1, this shunt current is now less. So the additional current which you have extra, you can put through IL. This is what happens stage by stage. When the output voltage decreases, Zener current decreases. Q2 conducts less, Q1 conducts less, which means it is pulling less collector current, which is the shunt current, which means the voltage drop across RS will also decrease, and you have more load current to provide, then you can bring the voltage up. We will use same equation for output. Vout equals VL, which is VZ plus the base emitter drop of the two transistors, VZ plus VBE2 plus VBE1. Any question from this part?
About the formula down. When are we gonna use it?
You will use it when you have this circuit. So you have to memorize some of the circuits.
You mean like the shunt one?
Yes, a shunt voltage regulator. There are two
Okay.
types of shunt. See, we studied two types of shunt. One is single Zener, single transistor. Output is VZ plus VBE. You have one Zener, two transistors. It is Vout is VZ plus, you can say 2 times VBE. We assume both transistors are silicon, so they are both 0.7. For two transistors, you have 2 times VBE, voltage drop. And for any other thing that we studied, series voltage regulator, current limiting, each one has different configuration, so the formula is different. For current limiting circuit, we don't provide the output equation through the loop because it is done in terms of current limiter. But if you know IL and RL, you can just write Vout equals IL times RL. We come back before, what is the series voltage regulator? In this case, you have to remember, I think this one is given in the formula sheet. This is one transistor and one op amp, one Zener. You can actually, if you forget the formula, you can actually take V plus equals V minus. So you can say VZ equals Vout R2 divided by R1 R2. You can finally get this formula. And previously, I'm going back again. This one is what? This formula is right here. V equals Vout R2 divided by R1 plus R2. V2 also equals VZ plus VBE2 from the bottom loop. So once you see a circuit, be able to recognizing that is important. A shunt voltage regulator, we call this discrete voltage regulator. Why discrete? You are just adding, you are picking some component maybe from the circuit lab or electronics lab. You can add all of them on a breadboard or solder them on a PCB. This is called a discrete voltage regulator, individual elements. But we also know about integrated circuits, IC. Inside the IC, you can create maybe thousands or millions of transistors. It is possible. So if you don't want any of the trouble of adding all these components, you can just buy a regulator, voltage regulator IC. Inside the IC, everything is already designed and connected through fabrication in the factory. Inside a voltage IC regulator, you'll find a few things. If you go inside the IC design, from outside you cannot see anything. From outside you just see maybe a black body with 8 pins or 4 pins or 6 pins, whatever the IC is that. Inside you already have comparator circuit. It has a comparator inside. It has a reference voltage in the IC. It has control mechanism inside, also overload protection from high voltage and high current. Typically, the IC voltage regulators are 3-terminal regulators. You don't have an IC with 3 pins. It doesn't look pretty and it doesn't sit well in the connection. When the companies make ICs, they have to make symmetric. If you have 4 pin on one side, there will be 4 pin on the other side. I have never seen an IC with 3 pin on one side and 2 pin on the other. For aesthetics means for the sake of beauty and presentable, it has to be symmetric. Sometimes for that reason, some of the pins of the IC are not used. So there are 3 types of 3-terminal IC voltage regulator. You can provide a fixed positive voltage value, which means if you buy a model that gives you plus 5 volt, it will give you plus 5 volt. You can get a 12 volt, 10 volt, 20 volt, whatever you want to choose. In some applications, you might want to provide a negative regulated DC voltage. You can find negative voltage ICs as well. And you can even get adjustable voltage regulator by using ICs. So, basic diagram of 3-terminal voltage regulator. If you buy an IC like this, you have to look at the spec sheet because there are some important parameters. What are the important parameters? First is the range. What range of input voltages can you control and regulate? And it has to be compared for a specific range of output voltage and load current. You cannot provide any type of input voltage to an IC. You have to look at the spec sheet, see what is the range of input voltage, allowable input voltage, which will give you a specific range of output voltage and load current. It is important to be within that spec. There is another term you should find on the spec sheet of a voltage regulator ID. It is called the load regulation. There are 2 regulation parameters. One is the load regulation and the other one is line regulation. Load regulation gives you an idea how much variation you can have in the output voltage if you have some variation in the load current. How much it can control properly. So load regulation refers to the load side. If the load is disturbed for some reason, maybe it becomes short circuit or it is faulty, it will try to affect the load current. Variations in the load current will also try to affect the variation in your output voltage, which you do not want. So this amount of variation in output voltage with respect to the load current variation, we call it load regulation. How else can your regulated output change? We talked about possible disturbance in the load side, but sometimes The input side may not be smooth. Also, there might be some problem. Supply problem, maybe the voltage is too much down, or sometimes you have a spike on the input side. That's why we also have to use, in our houses, we use multi-plugs, which has built-in overload protection. So if you have some disturbance on the input side, we call it the variations in the input voltage. The input voltage is not according to what you have guessed due to some reason. How much variation will you see in the output voltage when you have variations in the input voltage? We call it the line regulation. So one is the load regulation, one is the line regulation. If we now look at the generic connection diagram, it is a generic, means we did not use a specific IC, just showing how it is connected. For a voltage regulator IC, you have an input pin. On the input pin, or in, you have to provide the unregulated DC, which is coming from your filter. After the filter stage, you have voltage regulator IC. This is coming from the filter, you put it in on the input pin. The output pin is supposed to provide you a steady DC voltage with certain amount of current. You just connect it with the load, and then ground, you connect on both sides. So the third pin of the voltage regulator that we have to use is a ground pin, in, out, and ground. What are some of the ICs that we can use for voltage regulation? Before we go to the models, now we can look at a more specific type of circuit. This is a fixed positive voltage regulator. The output you will get from this IC is a positive volt. Can you guess how many volts from this one? So there are 3 pins, 1, 2, and 3. See, the input is coming on the in pin. The output is in the output. You have a ground. This is called IC 7812. It is a series 78 IC voltage regulator. The first 2 letters of this one will tell you the name of the series. The last 2 digits will give you the voltage. So series 78 and 12, then you have IC 7812. It will provide you a positive 12 volt. That's a fixed positive voltage regulator. The unregulated input voltage is filtered by capacitor C1, which you have then a voltage with slight amount of ripple, which is the wavy shape. The output provides a regulated 12 volt DC. You might ask now, we have already had a capacitor in the beginning. On the input side, it's a wavy form still. It is regulated output. Why do we need the second capacitor on the output side? There's a reason for that. You need to filter it. The output has to be filtered when or for what reason? Mostly for high frequency noise. All of our circuits, they can pick up some noise from the other part of the circuit board or even from the environment. And the noisy signals, usually they tend to be high frequency. We don't want this noise to show up on the load side. So if you have a capacitor C2, you can filter out noisy signals on the output. This output V voltage, which is now at this moment 12 volt for this example, it should remain constant within the voltage variation limit. So you cannot do whatever you want. You cannot provide as much input as you want, and you cannot expect it to stay safe if you vary the input outside of your spec. There's a voltage variation limit. We talked about line regulation and load regulation. For certain amount of input voltage variation, the line regulation will take care of the providing of constant output. For certain amount of variation in the load current, the load regulation factor will also take care of providing you the fixed DC output. But if you go beyond that, if you go beyond and above that limit, it cannot help. So the designer has to think a bit advanced, a bit ahead. What can possibly go wrong in your actual real life application? This is a table that shows you the different models of voltage regulator ICs with their corresponding output voltage. See, it starts, the part number starts with 78. So it's series 78. The last two digits will give you the regulated output voltage that you can get from the IC. You have 78, 05, 06, 8, 10, 12, 15, etc. So 5 volts, 6, 8, all the way to plus 24. If you have a negative voltage regulator, it will give negative. There will be notations which will tell you that it's a negative one. Minimum VI. What is the minimum VI? It means in order to operate this IC, you have to have at least, so pick 7805. You want a regulated plus 5 volt DC throughout its operation. It needs a minimum VI, which is on the input side, 7.3 volts. To get 5 volts, you need 7.3 volts input. Look at the last row. If you want a 24 plus 24 volt output DC, regulated steady, on the input side, you need 27.1 volts. So the output voltage is less than the minimum voltage required for the IC to operate properly. For a fixed negative voltage regulator, if you pick a negative voltage regulator model, I have never used a negative voltage in any of my projects. I use only 78 series. So I don't know if any of you are using it in your senior projects or not, but if you buy this type, the connections are the same. On the input side, you have unregulated DC. On the output side, you have regulated DC, but it will be a negative level, below zero. The 3-pin connections remain the same, in, out, and ground. Line regulation and load regulation, they both apply. And you can have an adjustable voltage regulator. This is a different model, as you can see. The output voltage from this IC is not the same, like not fixed. You can change it. There are 3 pins, input pin, output pin. The third pin is called adjust. So you connect with external components like this. You have 2 resistors, R1, R2. You're taking the output from the top to bottom. You can pick the R2 to be a variable resistance or a potentiometer. And then you will be able to change the output voltage. LM317 is the model of this IC. LM, I think it comes from a company called Fairchild Semiconductors. Fairchild Semiconductors, their IC names usually start with LM. So what output voltage you want, you will select your output voltage using a potentiometer within a certain range. Adjustable voltage regulator. Draw its voltage supply using a full wave bridge rectifier capacitor filter IC regulator. I intend to give you a similar problem like this for your fifth homework. Your fifth homework will be assigned tonight, giving you a 1 week deadline, which will be next Thursday. So on that homework, I pick problems from this. For the fifth homework, there are 2 chapters included. The first one is feedback and oscillator circuit, which is the previous chapter. I have not given you homework from that one yet. And there will be 3 problems from chapter 14. From this chapter, chapter 15, I usually give 6 problems, which are short problems. A total of 7 problems for your homework assignment number 5. That will be your last homework assignment. The next 2 chapters, other 4-terminal and PN devices, they are more like descriptive. You have to memorize and remember a lot for the last 2 chapters of this course. So not much problem solving, but conceptual. Maybe you have to read a graph and tell what is going on. For example 1512, if you want to draw, how will you draw? It says you need to use a full wave bridge rectifier. What I recommend is first use a main supply and a step down transformer. Main supply, our RMS voltage for a single phase is 220. And then on the secondary side, of course, you cannot provide 220 volt to diode, it will burn. So use a step down transformer. If you need a full wave bridge rectifier, there has to be 4 diodes connected in bridge configuration. Be careful with the orientation of the diode with the anode and cathode. You have to make sure that during the positive half cycle, 2 diodes are on, another 2 will be off. And during the negative half cycle, the other 2 diodes are on and the first 2 diodes are off. After the rectifier, you can just give 1 capacitor. There is no need to do RC. If you want to be more sophisticated, after capacitor filter, you can add additional RC stage. It is optional, not necessary. The output from the filter stage, you can put on the input pin of the 78. In this case, we need plus 5 volt output. So your IC model will be 7805, 7805. And then the output will be connected to a second capacitor in order to filter out any high frequency noise signal. The ground will go to ground. You can also pick the ratio of the transformer winding. Primary side, secondary side, how many coils you want on the primary side, how many coils you want on the secondary side. If you want to design, put the ratio of the primary and secondary winding, you have to know the relation. V1 over V2 equals N1 over N2. So for a step down transformer, V1 is high, V2 is low, means N1 will be high, N2 will be lower value. That's a step down transformer, right?
Teacher, did you draw anything? Nothing, right?
No, I didn't draw anything. I'll give you a
Okay.
homework to draw, but I'm just telling you how to do it. I think, what is the next slide? Practical power supplies. Where do we use a power supply? DC supply. The adapter of the laptop is a perfect example for that, or the adapter of anything, your television, laptop, even the charging adapter for the cell phone and tab. They have all the components of a good power supply inside. They have step-down transformer, rectifier, filter, and IC regulator. Otherwise, you will not have a steady charge. You will have a very unstable voltage coming out. It will later on damage your equipment. Switching power supplies are called chopper supplies. There you can have power supplies. It's not the topic of this course. And then battery charger I mentioned. TV horizontal high voltage, I don't know what it means because I've never worked on this thing. So wait until the evening. I will give you the instruction for the quiz as well. Even though I think you don't need it, it is the same as quiz 1. For quiz 2, it will be on Tuesday. You'll be given 1 hour. We have how many classes left? We have, okay, Tuesday will be quiz, and then Thursday is a class. Then you have next Tuesday and next Thursday, 3 more classes. I think we can start the next chapter, and with the 3 more available classes, we can finish. So quiz 2 next Tuesday, starting at your class time, you will be given 1 hour. It will be done through a Google form, just like your quiz 1. You have to use your university username and password. Do not sign in with any other Google account. Do not use, if you are in a shared dorm and you and your friend both are the same students, same university, do not use your friend's account. So your ID will not show up when you submit with a Google form. It is open to AU students. It has to be submitted by only you. The topic of the quiz will be everything from after the midterm until today. I don't think I asked anything from power supplies because power supplies is fairly new, but it's safe to study a bit. I think voltage regulator questions might be there. I can't exactly remember how many questions, maybe 10, 12, but you'll be able to do within 1 hour or less than 10. I will post this instruction as a PDF file on Microsoft Teams. And at the same time, I will assign you the homework, which should be within this evening. Is there any specific thing or question from this chapter that you want me to repeat? Or you'd like this to be for the last class, if we could do a review?
Teacher, so this is the last chapter?
No, there are 2 more chapters, which is combined in one slide. I will
Okay.
start a little bit of introduction now, because we should go for at least 15 more minutes or 20 more minutes. So let me see, I'm trying to locate my lecture presentations. We have chapter 16 and 17. Let's open this chapter. The semester is almost over. So for any time conflict students, I know there are 3 time conflict students from this class for the final exam. One student, he said his teacher will never change the time. For the other 2 students, if you could do the same for what you did in the midterm, that would be great. Otherwise, you will have to take the exam in the evening at night. Your final exam is on Friday, March 18, from 1 until 4. If the time conflict cannot be managed, maybe you have to take exam from 4:30 until 7:30 or 5 until 8. I would rather not have an exam on Saturday, Sunday. This might be your break or study time. Morning time is kind of tricky because I have other appointments. So please check your time conflict for the final exam. This is chapter 16. So beginning of the last two chapters, chapter 16 and 17, other two terminal devices. What are the other two terminal devices? These are some names. Schottky diodes, varactor, power diodes, tunnel diodes, photodiodes, photoconductive cells, infrared emitters, IR emitters, LCD, solar cell thermistor, which is a resistor that responds to changing temperature. What is the basic two-terminal device that we studied? In the beginning of this class, we started with diode, a p-n junction diode. Why do we study these last two chapters? In this world, we have a number of two-terminal devices which have a single p-n junction, just like your regular p-n junction diode, or a Zener diode, which also has two terminals. Yet their modes of operation are totally different from the basic diode. Their terminal characteristics are also different. The areas of applications are also totally different from the basic diode and the Zener diode. That's why we need to study a bit about these. The last two chapters are a lot about memorizing, more descriptive, not too much mathematical. In addition, some of these two-terminal devices, they were constructed using different manufacturing techniques, different from what people do for regular diodes. Photoconductive cell is a two-terminal device which has different construction. LCD and thermistor, they are different. I'll just quickly introduce Schottky diodes today. This is the symbol of a Schottky diode. The name Schottky comes from the name of the person. And you have seen for the JFET chapter, there's a JFET transfer curve, which is called Shockley curve. Schottky and Shockley, they sound the same. They're not the same. Two different persons. There are other names for the Schottky diode. It is known as the hot carrier or surface barrier or Schottky barrier. It looks somewhat like a Zener, but it's not exactly that. This is the symbol for the Schottky diode. In the earlier days of Schottky diode, the application was limited to ultra high frequency applications because the Schottky diode has a very quick switching time. Remember the diode turn on and diode turn off response time, reverse recovery time for the basic diode. For this one, the response time is very high, very quick. I mean, very quick, not very high, very quick. So it's a low number. The noise is lower. If you want an application which is in ultra high frequency or very high frequency range, both the switching time and the noise reduction is important. But in recent years, the Schottky diode appears in more and more different applications. For example, low voltage, high current power supply and AC to DC converters. Other areas may be radar systems. One is called a Schottky TTL logic. That stands for transistor logic. So you have a low level 0, high level 5 volt between certain voltage you have a binary 0, and for some high voltage you have a binary 1. That's a transistor logic, analog to digital converter, mixer network. I would like you to actually carefully look at this characteristic graph for the Schottky diode. The black dash, do you see the black dash line?
Yes, we can see it.
This is your regular PN junction diode we studied in chapter 1 and chapter 2, diode and diode application. So silicon, germanium, gallium arsenide, etc. You see, when does it start conducting? Around 0.6, 0.7 volt, all the current comes up. If you put it in the reverse bias situation, you see, you can apply really, compared to the Schottky diode, you can apply a high reverse voltage before it will start breaking down. Now it's going in the Zener region. The blue line now is the Schottky diode. Only around 0.3 volt you have full conduction. What is the reverse saturation current? Look at the two levels. The regular PN junction diode has certain amount of reverse saturation current. This one has larger current in the reverse direction. When does it break down? It can break down before the PN junction diode. So construction is different from the regular conventional PN junction diode. How? We'll come to that soon. But the different construction techniques, it results in different set of characteristics. What are the different characteristics compared with the regular diode? Increased frequency range, the bandwidth will be higher. Lower forward bias, which you have seen from this graph, the forward bias voltage for the Schottky diode will be lower compared to your regular diode. In general, it is constructed in such a way that you have a more uniform junction region and high level of ruggedness. It's strong. It can be operated in harsh conditions. So what we have seen from the graph, the forward bias voltage is less. You know what is the meaning of forward bias voltage? The voltage is the potential difference. It's like an energy that you have to supply for the conduction carriers to flow. In between, for the regular diode, you have a depletion region, which is like a wall. You should have enough potential energy for the carriers to break through the wall and flow. This one, it needs less. Why? I'll explain this, quickly mention. We have also seen on the bottom left, the peak inverse voltage, PIV, or peak reverse voltage. It occurs earlier than the PN junction diode. Reverse current has a higher magnitude than the reverse current of the PN junction. So why it can conduct early in the forward bias? Because the barrier at the junction for a Schottky diode is less than that of the PN junction diode. And this applies to both forward and reverse situation. What happens to the depletion region when your PN junction is forward biased? Only a little bit, right? If you do not bias it, no bias, moderate. If you reverse bias the PN junction diode, what happens to the depletion region? It becomes wider. But this one doesn't happen with the Schottky diode. For both forward bias and reverse bias condition, the barrier or the wall that we imagine as an imaginary wall, the barrier is much less than the barrier at the PN junction diode. This is why when it is in reverse bias, the Schottky diode is able to carry a lot of current. It is a desirable situation in the forward bias, but this is you can say both as an advantage and a disadvantage. The ability to carry high current easily early. For the forward bias situation, we don't have a problem. But this ability or advantage can become a disadvantage in the reverse bias condition. You really have to watch out because soon it enters the breakdown region. Now I remember who's the person behind this Schottky diode. His name is Dr. Walter Hermann Schottky, a German research physicist. What about the reverse recovery time for the Schottky diode? How fast this diode can switch from conduction to no conduction? Let's compare the two numbers. For a PN junction diode, you can take several microseconds, maybe 100 nanosecond. The Schottky diode, from conducting to no conducting and back to conducting, if you want that, it can be 100 picosecond. Pico is 10 power negative 12. You can go to 10 nanosecond. That is larger than picosecond. You can be as fast as 100 picosecond. Do you know why? Because we are talking about the recovery time, but for the case of Schottky diode, there is really nothing to recover from. There is no depletion region. It's because of the construction technique, it's negligible, it's not there. So here on this slide again, it says low forward voltage drop. It stays between 0.2 to 0.63 volts. You can have a very high forward current. See the value, 75 ampere. In my lab, I use a 1 ampere fuse. 75 ampere is very high. It's a high current application. 1 ampere current can kill a human. If you take 1 ampere of current for 4 seconds, your heart will stop. This is 75 ampere. And we discussed significantly lower peak inverse voltage. The reverse current is high, switching rate is fast. As I've said, it can be 100 picosecond. We don't talk about varactor diode today. We have plenty of time to cover the rest of the course using the remaining number of classes. So this is an introduction to chapter 16. I will now call for your attendance before we conclude our today's session. So remember, next Tuesday is your quiz, and your instruction for quiz as well as the 5th homework assignment will come up within today evening. Mr. Balan,
Yes, sir.
Tirawut,
Yes, sir.
Napatra,
Yes.
Pakon. Is Pakon present? Rajay,
Yes, John.
Chonikan,
Yes ค่ะ
Michelle. Is Michelle present? Phil,
Here, sir.
Silicon,
Yes teacher
Visalut,
Yes, sir.
Yu Cheng,
Yes, teacher.
Sesihan,
Yes, sir.
Patampong,
Yeah,ครับ
Kongsu,
Yes, John.
Martin,
Yes, John.
Kolawik,
Yes.
Pichayut,
present ครับ
Jimma,
Yes, sir.
Sonyuan.
Yes.
What day is today? Is it 24 or 25? 24, right?
24.
Satavat,
Yes.
Yapeng,
Yes.
Seni,
Yes, present.
Siripo,
present ครับ
Vitu,
Yes.
San An.
Yeah.
Waramet,
Yes.
Nabawan,
Yes.
Natapop,
Yes.
Warapat,
Yes.
Nataya,
Yes, teacher.
Pichayapon, Miss Pichayapon, maybe offline. Komchan, is Komchan present? Piradon,
Yes, present.
Kitsanapong,
I'm right here, Chair.
Atitya,
Yes.
Tasin,
Yes, I'm here.
Sukaina,
Yes, teacher.
Sirin,
Yes, teacher.
Min Luin O. Somebody is sending me a message in the chat. Pichayapon, I could not hear you. Okay, I'll give you attendance. Anyone else missed? Yeah, microphone didn't work out. Sometimes we have a delay. So, is Michelle here?
Yes, I can.
How about Pakon? Pakon is not here today. Michelle is here. I don't see any other absentees. So, see you for the quiz on next Tuesday.
Thank you, teacher.
Welcome.
Thank you, sir.
Thank you. Thank you, teacher.
Okay, have a good weekend, everyone.